My name is Bindel, and in this video I will present joint work with John Schanck about decryption failures of lattice-based encryption schemes. Our paper has been accepted at PQCrypto 2020. The security of lattice-based encryption schemes is often ensured by a security reduction from a computationally hard problem and a concrete hardness estimates of this problem. An example for a hardness assumption that is relevant also in this talk is the learning with errors problem. In this problem, a matrix A is sampled uniformly random in C modulo Q. Furthermore, a secret and error vector are sampled with discrete Gaussian distribution, and a vector B is computed as B equals A times S plus E modulo Q. Given the tuple AB, the learning with errors problem is to find the vector S. Interestingly, the security of lattice-based encryption schemes also rely on the probability of finding a decryption failure. Calculating this failure probability is the topic of this talk. In particular, the contribution of our paper is to consider the information that is gathered by adaptively asking queries, and we consider this in both the theoretical and practical analysis. But let's take a step back and let me introduce a generic LWE-based encryption scheme first. The key generation is very simple. First, you sample the secret key S and E. Then, the public key A is sampled and B is computed. Given the public key and a message M, the encryption consists of two steps. The first one is to compute another learning with error sample using A but a different S' and E'. In the second step, B and S' are multiplied and another error E' and the encoding of the message M are added. Given the secret S, C and C', decryption works as follows. Since B times S' is about the same as C times S, the decoding of C' minus C times S returns M. At least, as long as B times S' and C times S are approximately the same. But how close do they need to be? In the Frodo NIST submission, for example, the following statement is made. Let Q be a power of 2, then the decoding of an encoded K plus some error E gives back K as long as E is in between these bounds. For our generic encryption scheme, this means as long as the sum of the error and the secret terms, which corresponds to E, is in between these bounds, the decryption returns back the correct message M. That means every decryption error tells us that the sum of these error terms is larger or smaller plus minus Q divided by 2 to the power of B plus 1. And gathering many decryption errors gives the ability to recover the secret S. That said, an attack could try to trigger a decryption error with higher probability. And indeed, this is what the original so-called failure boosting attack does. It was published at PQC in 2019. Another interesting work from Decryption 2020 shows that after one decryption failure is found, it actually gets easier and easier to find more decryption failures. So really, decryption errors should be prevented. Interestingly, if we know that a scheme is not perfectly correct, also every successful decryption tells us something, namely that the error terms are in between these bounds. That means we can even gather information from successful decryptions. This leads to our first contribution, the refinement of the failure boosting attack. In particular, in our analysis, we consider adaptively collected information from successful decryptions. Let me visualize the idea of our refinement. Recall that the secret key is given by S and E. Moreover, the ciphertext consists of C1 and C2. Furthermore, let's consider a sphere and assume that the normalization of the secret S is somewhere on this sphere. Now an attacker can choose some randomness. That means he can choose some S', E', and E double prime, compute the corresponding ciphertext, and ask the encryption to a decryption oracle. The oracle then returns a decryption failure or a successful decryption. That means from a successful decryption, the adversary learns that the secret S is not in the blue area corresponding to the randomness epsilon1. And also, it's not in the blue caps corresponding to all the other successful decryptions. That means, to trigger a decryption failure with higher probability, the next blue cap corresponding to the next query should have as little overlap with the blue area in the sphere, on the sphere as possible. Or to put it differently, the adversary should choose the randomness epsilon A in the red region. Depending on how the adversary chooses the randomness, the query set is more or less efficient. Let E be the set of randomness used in the decryption queries. Then the efficacy of the query set is essentially the fraction of the sphere covered by the caps, so the blue area divided by the area of the sphere. One can assume that an intelligent adversary would try to increase the efficacy while decreasing the number of queries at the same time. The cost of an adversary then consists of generating the efficient query set and the cost of asking these queries. In this slide, you can see our experimental results. We analyzed different camps from the NIST post-quantum standardization effort. On the left-hand side, you can see the predicted size of a query set of unit efficacy. That means that given a query set of this size, the attacker will find a decryption error with probability 1. On the right-hand side, we show the cost of producing such a query set. You can see that if the adversary chooses larger and larger errors, the size of the query set becomes smaller. Intuitively, the adversary can cover the sphere with a smaller number of queries since the corresponding caps are larger. However, you can see that the cost of producing such a query is getting larger after a local minimum, because it is getting harder to find useful queries. So, one way to analyze the decryption failure probability is to estimate the cost of state-of-the-art decryption failure attacks. This approach leads to the smallest parameters possible, but for example, a new failure boosting attack would also lead to a re-evaluation of existing parameter sets. Another way to analyze the decryption failure probability is to use security reductions. The Fujisaki-Okamoto transform gives a tool to transform a passively secure randomized delta-correct public key encryption scheme into a de-randomized public key encryption scheme. Höfelmans, Hofheinz, and Kills prove that the resulting scheme is then a QG times delta correct public key encryption scheme, where QG is the number of queries made to the random oracle G that is used to de-randomize the scheme DP. Using this proof makes the parameter choice independent of new attacks. However, it also leads to larger parameters compared to the first method. So let's check how this is done in reality. Let's take Frodo Cam as an example again. I already showed this statement in an earlier slide. It states the correctness requirements. From this statement, the failure probability of the INCPA secure encryption scheme can be analyzed. However, when analyzing the correctness of the INCCA secure CAM, the authors refer to the section 2.27, and we are not aware of a proof for this statement. The reason that they refer to the INCPA correctness is of course the need for efficient parameters. This motivates our second contribution. We propose a new correctness definition that is tailored for de-randomized schemes. In this definition, we consider adaptively queried decryption queries. Let me take a step back and explain the current correctness definition by Hofheinz, Höfelmanns and Kitz. In this game, first, a public secret key pair is chosen, which are both given to the adversary. The adversary then returns a message M, which is encrypted by the challenger, to the ciphertext C. If the decryption of C gives back M, the game returns 1. The scheme is called delta correct if the probability that the game returns 1 is less or equal than delta. This is equivalent to the expectation over the keys and over the maximal probability that the decryption does not return M. Given that there is no dependency on M, this is equivalent to the probability that the decryption does not give M back over the random keys. We call this one the one-shot probability, because the probability is considered only for one random key pair and not a decryption of several ciphertexts for the same key pair. This, on the other hand, is the definition that we propose in our paper. Let me point out the differences. Instead of giving the adversary access to the secret key, the adversary gets access to a random and a decryption oracle. This is inspired by the INCCA security game. Moreover, the adversary of HHK is not computationally bounded, while we explicitly bound our adversary by a computational time t. Hence, we call our probability the delta QDT decryption failure rate. Let me compare the probabilities corresponding to the three different definitions. Again, we are using Frodo as an example. The one-shot probability is 2 to the minus 144. This probability is used in the Frodo submission. The proven lower bound on the probability that comes from the Fujisaki-Okamoto transform is 2 to the minus 16, which is rather large. Our delta QDT definition gives a smaller probability of 2 to the minus 34. We are concerned about this. In the Fujisaki-Okamoto reduction from the CCA security to CPA security, delta is multiplied with rather large values. Hence, the security reduction for these specific parameters are less tight. Let me emphasize, however, that there is no known attack that would exploit this gap. Let me visualize this using our experimental results again. The very left point can be viewed as corresponding to the one-shot probability. What you can see in this diagram is that the failure probability that we determine, which is this line here, is slightly larger than the probability used in Frodo, namely the one-shot probability. But you can also see that both of them are well below the target probability of 2 to the minus 128 that corresponds to the targeted security level. Let me summarize. In this talk, I showed you the idea of a refinement of the failure boosting attack. Moreover, I introduced a new correctness definition for de-randomized encryption schemes. Our experimental results do not ask for a revision of parameters of NIST candidates, in particular also not for Frodo. But they do show that the one-shot probability is not reliable. We hope that our work stimulates discussion on what an acceptable data correctness is for various security levels. Our full paper can be found on ePrint under 2019-590. I would like to thank Katrin, Jan-Peters and Steve for discussions and support. Moreover, I would like to thank you for watching this video.